This is our first lecture on forecasting. All types of organizations, for-profit and non-for-profit organizations, and all functions and processes of all organizations need forecasting. For example, accounting needs forecasting for, say, break-even analysis and estimating profit and loss. Finance needs forecasting to have an estimate of cash flow and find the best sources for cash deficit and the best uses for cash surplus. Human resource needs forecasting for hiring, for training. Marketing needs forecasting to know what is the stomach of the market and what is the trend and seasonalities in the market, and use them for pricing and promotion policies. Operations needs forecasting for production planning, for inventory management, for scheduling. In our forecasting lectures, we talk about qualitative techniques and quantitative techniques. Regarding qualitative techniques, we just mentioned a technique called Delphi. For quantitative techniques, we talk about time series analysis and causal relationship forecasting. Regarding time series analysis, we talk about moving average and exponential smoothing. Regarding causal relationship, we may talk about linear and nonlinear, single and multi-variable regression. Finally, we will talk about some measures to find it out which forecasting technique is the best fit for our specific set of data. All forecasting techniques have four characteristics. The first characteristic is forecasts usually, and to be more accurate, are always inaccurate. They are most of the time wrong. There is a very tiny possibility that our forecast comes out equal to what really happens in reality. Therefore, we should always accompany our forecast with a measure of variability. And that measure of variability is usually standard deviation or variance. Whenever we forecast, we should say, our forecast for next year is this much, and the standard deviation of this forecast is that much. And the lower the standard deviation, the better the forecast. Third characteristics of all forecasting techniques is forecast for aggregate items are more accurate than forecast for individual items. Forecast for the total U.S. economy is more accurate than forecast for subsectors of manufacturing, agriculture, and service. Forecast for manufacturing is more accurate than forecast for car industry. Forecast for car industry is more accurate than forecast for Ford Motors. Forecast for Ford Motors is more accurate than forecast for Mustangs. Aggregate forecasts reduce the amount of variability with respect to the average forecast. We will later mathematically show these characteristics, but right now, as we can intuitively accept forecast for summation of two products is more accurate than a forecast for the individual product, because up of one product can be compensated by down of the other product, and our forecast come out closer to the average forecast. The fourth characteristics of all forecasting techniques is long-range forecasts are less accurate than short-range forecasts. Forecasts further into the future tend to be less accurate than forecasts for near future. As time passes, we get better information and make better predictions. Now I would like to give you an example on how enterprises may benefit from these characteristics of all forecasting techniques. The combined ports of Los Angeles and Long Beach, also known as San Pedro Bay ports, from the point of container handling are ranked 5th in the world after the port of Singapore and 3 ports in China. more than 50% of containers coming to the United States pass through San Pedro Bay ports. More than 1/3 of the containerized product consumed in all other states pass through these ports. The total value of trade is around $300 billion, creating around $30 billion in state and local taxes and 3 million full-time equivalent jobs. San Pedro Bay ports and Southern California need to retain their competing edge. Otherwise, other potential routes will take business from Southern California and its ports. What are the competing edges of Southern California ports? Deepwater facilities for post-Panamax ships which may contain more than 8,000 containers. State-of-the-art undock facilities to transfer containers between ship and train. Intermodal transfer between ship, truck and train. Consolidation and distribution facilities for transloading from 20 feet containers and 40 feet containers to 56 foot containers which are allowed to move on California roads. But as important as these capabilities, and maybe more important than these capabilities, are the two last characteristics of all forecasting techniques. If we want to transfer load from Far East to East Coast, it will take 4 weeks. To West Coast, it will take 2 weeks. And to mid-United States, something between 2 and 4 weeks. Now, if I'm going to ship loads from Far East to East Coast, I should forecast the demand of East Coast 4 weeks in advance. If I'm going to ship from Far East to West Coast, I should estimate the demand of West Coast 2 weeks in advance. So estimates of West Coast, because it is for 2 weeks in advance, is more accurate than forecast for East Coast, which should be for 4 weeks in advance. Look at the other property. Forecast for East Coast and forecast for West Coast and forecast for mid-United States, all of them are less accurate than forecast for the total demand in the United States. So instead of forecasting for East Coast alone in 4 weeks and West Coast alone for 2 weeks and mid-United States for 3 weeks, I will forecast the demand for all United States for 14 days, 2 weeks in advance. Then when I send the container here, in 1 day I may transfer it to anywhere in California, in 2-3 days somewhere in mid-United States, and in 3-4 days somewhere in East Coast. Therefore, instead of estimating the demand of East Coast alone, which is less accurate than the demand for the whole United States, and instead of forecasting it for 4 weeks from now, I can forecast it for 14 days plus 3 days, which is 17 days from now. Forecast for United States, for the whole United States, between 14 days and 17 days in advance, is much more accurate than forecast for the East Coast 4 weeks in advance, or forecast for mid-United States 3 weeks in advance. We said we will talk about different forecasting techniques, and first we talk about qualitative technique. Delphi is one of the well-known qualitative techniques in which we ask opinion of experts with respect to something. For example, we collect data from experts with respect to the demand for our product. Some of them may estimate the demand at this level and some at a very low level. We summarize the point of departures of these experts and send it to these people, and summarize points of departure of these people and send it to the pessimistic people, and try to collect the next round of opinions. In the next round, these people may become a little bit may bring their forecast a little bit lower, and these people, after hearing about the points of departures of optimistic people, may bring their estimates a little bit up. Again, we summarize opinion of these people, send it to the optimistic people, and summarize the ideas of optimistic people and send it to pessimistic people. And after several rounds, these people will converge somewhere, and this level will be assumed as demand for the coming year. Time series is based on analysis of the past data and try to find a trend for future. This can be done with respect to any variable of interest, but because we are talking about forecasting for demand, always our variable of interest is demand unless stated otherwise. Time series can show some systematic components and some random components. Random components, we can't do anything about them, but we can identify three types of systematic components. The first one is level, where we think our demand is. The second one is trend, how it will change over time, upward or downward. And the third one, if there is any seasonality. Systematic components, we can identify them and we can quantify them. Random components, we cannot do anything about them. That is why no forecast can come out exactly the same as actual, because we are living in a probabilistic world. Things cannot be 100% predicted. Regarding time series, we talk about three techniques: naive forecast, moving average, and exponential smoothing. In naive forecast for next period is equal to actual for this period. We use F for forecast and A for actual. T is this period, can be anything, 1, 2, 3, 4, 5. T plus 1 is the next period. So if T is 1, T plus 1 is 2. If T is 5, T plus 1 is 6. AT, actual demand in period T. FT plus 1, forecast for demand for period T plus 1. Naive technique is very cheap, very simple, easy. We can always use it as a base to compare quality of other forecasting technique. If quality of other forecasting technique is lower than naive technique, then we always use naive technique, which is the cheapest, easiest. However, usually other techniques perform better. Before going to moving average, let's compare two extreme points. In one extreme point, we may say my forecast for next period is equal to actual for this period. This is one extreme point. The other extreme point is my forecast for next period is average of all pieces of data for all earlier periods. Two extreme points forecast. One relies only on one piece of data, the other relies on all pieces of data. Obviously, between these two extremes, we can have some other techniques which rely on, say, 3 most recent pieces of data, 7 most recent pieces of data, 100 most recent pieces of data. 3-period moving average in period 7, is A7 plus A6 plus A5 divided by 3. We use this notation. This shows 3 period moving average, and this shows we are in period 7. So the most recent piece of data is 7. Then this is 1 period old, this is 2 period old. Later on we'll remove these 3, because when I write here 3, that means we are talking about 3 period moving average. 3 period moving average in period T, the most recent piece of data is 80. 1 period old is 80 minus 1. 2 period old is 80 minus 2. So I have 3 pieces of data divided by 3. That would be 3 period moving average in period T. 10 period moving average in period T is AT plus AT minus 1 plus AT minus 2 plus what? What is the last piece of data? So we are talking about moving average in period T, and we are talking about 10 period moving average. What would be the last piece of data? A T minus 10 plus 1, which is A T minus 9. N period moving average in period T is AT, AT minus 1, AT minus 2, AT minus N plus 1 divided by N. Then we assume that forecast for period T plus 1 is equal to moving average for period T. For example, if you are in period 10, and we are talking about 5 period moving average, 5 period moving average at period 10, we assume it as forecast for the next period, which is 10 plus 1, which is 11, and this is equal to A10 plus A10 minus 1, which is 9, plus A10 minus 2, which is 8, plus A10 minus 5 plus 1, which is A6, and here I have A7 plus A6 divided by 5. Now suppose we have data for 12 periods. We want to compute 3 period moving average and 6 period moving average for these data, and finally we want to forecast for the next period using 3 period moving average and 6 period moving average, and we would like to compare the quality of these two forecasts. On the left hand side of the screen I have 3 period moving average, and on the right hand side I have 6 period moving average. After 3 period I can compute 3 period moving average, which is 1366, and I have got these numbers by adding the first 3 periods and dividing them by 3. For 6 period moving average, again I add up the first 6 periods and divide them by 6, and then I can continue for all other periods. So if I am going to compute 3 period moving average for period 4, I can simply add these 3 numbers and divide it by 3, and I will get 1458. However, there is also a smarter way to compute 1458. I know that I have 1366 as moving average of the first 3 periods. So what is the difference between the moving average in the second 3 periods compared to the moving average in the first 3 periods? These two numbers are the same in both computations, but in the second 3 period moving average I have added 1576 while I have dropped 1300. In other words, in the first 3 periods I have 1300 plus 1356 plus 1442 divided by 3. In the second 3 period moving average, still I have 1356 and still I have 1442, but there is a 1576 also over there, and I have divided all of them by 3. So this part is common between the first 3 period moving average and the second 3 period moving average. While in the second period moving average I have dropped 1300 divided by 3 and I have added 1576 divided by 3. In order to obtain 1458 using 1366, all I need is to take 1366, add 1576 to it divided by 3, and subtract 1300 divided by 3. In other words, I have 1366 here plus 1576 minus 1300 divided by 3. 276 divided by 3 is 92. Therefore, 92 plus 1366 is equal to 1458. In order to obtain, for example, 2154, all I need is 2092, add the most recent piece of data which I have observed in period 11, and that is 2214, which is the most recent piece of data. And in my previous computation for 2092, I had these 3 numbers added to each other divided by 3. Therefore, the oldest piece of data is 2028 minus 2028 divided by 3. 186 divided by 3. And 186 divided by 3 is 62. And 62 plus 2092 is 2154. Now I can compute any new n-period moving average using the previous n-period moving average by a simple computation. I write down the previous moving average, add the most recent piece of data, subtract the oldest piece of data, and divide it by the number of periods. Here I have computed the first 6-period moving average by adding the first 6 pieces of data that I have and dividing them by 6. Now in order to compute the next 6-period moving average, all I need to do is to take the previous 6-period moving average, which is 1537, and then add to it something, drop from it something, and divide it by 6. What I should add is the most recent piece of data, 1996, drop the oldest piece of data, 1300, 1537, 696 divided by 6. 1537 plus 116, and this is equal to 1653. When I am talking about period 7, the oldest piece of data is for period 1. But when I am talking about period 11, the oldest piece of data now is A5. It's the time to talk about defining a measure of effectiveness to find the suitability of the forecasting technique to our specific set of data. Here I have a new set of data, and I have computed 3-period moving average and have assumed it as forecast for the next period. These are my forecasts and these are my actuals. How could I know if this is a good forecasting technique? Let me go through a simple example. Suppose these are our actual values for 4 periods. These are my forecasts for these periods. And for simplicity, suppose that the difference between actual and forecast in all periods have the same absolute value. This value and this value and this value and this value, they are all equal. However, here and here, forecasts are greater than actual, while here and here, the actuals are more than forecast. One measure of effectiveness to find if a forecasting technique is good for our data is to add the differences, to add the errors. So if I add these 2 values and then add to this and then add to this, because 2 of these values are negative and 2 of them are positive, the summation would be equal to 0. So that will tell me the forecasting technique is excellent because the summation of the errors have come out 0. Adding the actual values, these two negative values and these two positive values is not a correct procedure. I should find a way to remove the sign. No matter these values are positive or negative, I should remove the sign and add them together. There are two ways to remove signs. The first one, if I have a value of a, I can put absolute value of a and that will remove the sign. So if I have negative 2, the absolute value of negative 2 is positive. The other way of removing a sign is if I have a value of a, I can square it. This one also will remove the sign, because if I have negative 2, when I square it, it becomes 4. We stay with some of the absolute values and define mean absolute deviation, which is the summation of the absolute value of the difference between actual and forecast divided by the number of observations. Here are actual demands, here are 3-period moving averages, and here are my forecasts. So my forecasts start from period 4 on. In period 4, my forecast is 1382, my actual is 1470, the difference is 88. An absolute value of that difference is 88. In the second period, the actual is 1008, forecast is 1416, the difference is negative. I compute the absolute value of that negative number and I put it here. And I will do the same for all pieces of data. And then I will add all these numbers. All of them are positive values. And I have them for 9 periods. I add up these numbers and divide it by 9. And I will get 202. This is my MAD, mean absolute deviation. My forecast for period 13 is 1450, and mean absolute deviation of this forecasting technique is 202. Mean absolute deviation serves two important purposes. I can use it to compare 2 or more forecasting techniques and find it out which technique is better. Is standard deviation of forecast is equal to 1.25 times MAD. Now I have my FT as my average forecast for the next period, and also I have MAD multiplied by 1.25, which is the standard deviation of my forecast. So using 3-period moving average, my forecast for next period is 1450, and my standard deviation of forecast is 202 multiplied by 1.25, which is equal to 250.25. Let's just write 250. My forecast for the next period has normal distribution with mean of FT and standard deviation of 1.25 MAD, which in this specific case, my forecast for period 13 has average of 1450 with standard deviation of 250. Therefore, I can expect that the actual demand for the next period with more than 99% probability to be between 1450 minus 750 to 1450 plus 750. And that is a characteristic of normal distribution. More than 99% of observations will be between mean plus 3 standard deviation and mean minus 3 standard deviation. Let's summarize. For each period, I will find the difference between actual and forecast and then remove its sign. Then I will add them up and then I will divide it by the number of observations. This would be my MAD. Standard deviation of my forecast would be 1.25 times MAD. I can use MAD to serve two purposes. The first one, to find it out which forecasting technique, 3-period moving average, 6-period moving average, 9-period moving average, 13-period moving average, which technique is the most appropriate technique for our specific set of data. The most appropriate technique is a technique which has the minimum MAD. And the second application of MAD is standard deviation of my forecast is equal to 1.25 MAD. However, when I compare two or more forecasting techniques, I should compare them over the same number of periods. Now I have this set of data and I want to know which technique, a 3-period moving average or a 6-period moving average, is more appropriate for this specific set of data. So I compute 3-period moving average, and in each period I will have moving average for that period equal to the forecast for the next period. I also compute 6-period moving averages, and moving average of each period is set to the forecast for the next period. For 3-period forecasts, I have my forecast from period 4 on. For 6-period forecast, I have my forecast from period 7 on. But when I compare two techniques, I should compare them over the same number of periods, because here I don't have 6-period forecasts, so I drop this set of data. And I will compare the two techniques from period 7 to period 12. For each period, I will find the difference between actual and forecast, and if it is negative, I remove the sign. I will do the same for 6-period moving average. I will find the difference between actual and forecast, and if I have negative sign, I remove. Using 3-period moving average, my forecast for next period is 1450. Using 6-period moving average, my forecast for next period is 1590. Which one is better? The forecast cannot tell us anything about which one is better. That is MAD which will tell us which technique is better. 3-period moving average has a MAD almost 160. 6-period moving average has a MAD 195. 160 is less than 195. For this specific set of data, 3-period moving average is better than 6-period moving average. Our forecast for period 13 has a mean of 1450, and the standard deviation of this forecast is 1.25 times 160, which is 200. Therefore, forecast for the next period is normally distributed with mean of 1450 and standard deviation of 200. Here is our data, actual data, 3-period moving average and 6-period moving average. The longer the number of period, the smoother the data. The smaller the number of period, the more reactive the forecasting technique to the recent changes in the actual data. For this specific example, 3-period moving average performs better than 6-period moving average. Should we always use as many as periods we can? We don't know. The measure of effectiveness is MAD. The forecasting technique with lower MAD is the better technique. Now let's look at another set of data. This is a different set of data for which we have computed 6-period moving average and 3-period moving average. And we can compare them from period 7 on. 3-period moving average has a forecast of 1590, 6-period moving average 1540. These are just average forecasts. These are just average forecasts, and we cannot judge two different techniques based on their forecast. We need to look at MAD. For 3-period, MAD is 293. For 6-period, MAD is 254. Therefore, for this specific set of data, 6-period moving average forecasting technique is a better fit because it will end up with a lower standard. Because it ends up with a lower MAD. Our forecast for next period has an average of 1540 and standard deviation of 1.25 times 254, almost 254, 317. Average 1540, standard deviation 370. Again, as we see, 6-period moving average is more smooth and 3-period moving average is more reactive. The larger the number of periods, the smoother the curve. If you are a long-term investor, you look for larger number of periods to smooth the forecast and see what the general trend is. If you are a day trader, you stay with smaller number of periods to be more reactive to the most recent changes in data. Here I have shown 5-day, 20-day, 50-day and 100-day moving average for Microsoft stock. As you see, 5 days moving average is more reactive to the most recent changes. 100 days moving average is smoother and shows the general trend. For example, if you are here and you want to put some money in your 401k, you realize that Microsoft is not a good investment. But as you move in these periods, you see that it's not a bad idea if we invest a fraction of our 401k in Microsoft. Again, here we may think it's not good to invest more. We said our measure of effectiveness to select a technique among several techniques for our forecasting is MAD. The lower the MAD, the better the forecasting technique. Now we define a second measure of effectiveness which can help us to find it out if our forecasting technique is reliable. Reliability means quality over time. Reliability means that the forecasting technique is good and it will remain good over time. We define tracking signal as summation of the difference between actual and forecast. So we keep the sign. If actual is greater than forecast, the sign is positive, otherwise it is negative. Divided by MAD. And because MAD by itself is summation of the absolute value of the difference between actual and forecast, divided by the number of periods. Then if I replace MAD with this equation, I will get this one. Note that MAD is always positive because it is summation of actual minus forecast with absolute value signs divided by the number of periods. Therefore, MAD is always positive. But the numerator of tracking signal could be positive or negative. So tracking signal by itself could be positive, could be negative. Here I have a set of data and here are my forecasts. To come out with these forecasts, I have simply assumed that forecast for period 2 is equal to actual for period 1, and then in each of the future periods I just have added forecast and actual and have divided by 2. For example, I have got 685 by adding the actual of the previous period to the forecast of the previous period and divided by. But that is not our concern right now. Suppose using an unknown approach I have come out with some forecasts. Therefore, here are my forecasts and here are my actuals. These are the absolute value of the difference between actual and forecast. 720, 685. The absolute value of the difference is 35. And so on. Then I have added these two numbers and I have added all these numbers and I have put it here. Here I have divided 10 by 1 and I have got 1 as MAD in the first period. The summation of the absolute value of the difference between actual and forecast for the second 2 period is 45 divided by 2, 22.5. Summation of the absolute value of the difference between actual and forecast for all 8 periods from period 2 to period 9 is 261.5. I have divided by 8 and I have got 32.7. This is MAD for the last period. This is MAD for the first period, which is indeed my period 2. Here I have done the same computation, but I have not removed the sign. So the difference between actual and forecast is minus 10. And then I have found the difference between actual and forecast for all periods. This 5.6, I have found it by adding all these numbers. This negative 26.8, I have found it by adding all these numbers. If I divide 5.6 by MAD of that period, which is 32.4, I will get 0.2. If I divide negative 26.8 by MAD of this period, I will get negative 0.8. What do you expect tracking signal to be? What value? 1000, 5000, 100, negative 100? What? Positive or negative? The expected value of tracking signal is sometimes actuals are greater than forecasts, sometimes forecasts are greater than actuals. Therefore, the expected value of a set of random positives and negatives is 0. 0 divided by a positive number is 0. This is my tracking signal for period 1, for period 2, for period 3, and so on and so forth. We have a upper control limit and a lower control limit. Tracking signal should have two characteristics. First, it should remain between upper control limit and lower control limit. Second, it shouldn't show any specific pattern. When we look at tracking signal over time, it should completely look random, no specific pattern. So this tracking signal is okay. This forecasting technique is reliable because the tracking signal is between the upper and lower control limits, and because I cannot extract any pattern. If tracking signal is out of upper control limit or lower control limit, then the forecasting technique is not reliable. However, even if it is within control limits, it may also not be reliable. For example, in this case, tracking signal is positive and remains positive. It is always greater than 0. Tracking signal is the difference between actual and forecast. Sum it up, divided by a positive number. So this is always positive. If tracking signal is always positive, that means actual is always greater than forecast. Like this case, summation of the differences between actual and forecast is always positive. Actual is always greater than forecast. We are underestimating the demand. In a case like this, we clearly see a pattern, a seasonality pattern. In some periods, actuals are greater than forecasts. In some periods, forecasts are greater than actual. So either there is a seasonality in the real world, in our actual demand, which we have not incorporated it into our forecasting technique, or we have incorporated the seasonality into our forecasting technique, which does not exist in reality, is not a systematic component of our demand. Seasonality doesn't need the actual season. We can also have seasons of less than 3 months. For example, demand for movie theaters is seasonal. We have high season in Friday, Saturday, and Sunday, and low season in other times. Demand for public transportation is seasonal. It is high season, for example, between 6:30 and 9:30 in the morning, and 3:30 to 6:30 in the afternoon, and low season in other times. So we talked about MAD and tracking signal to make sure that our forecasting technique has good quality and that quality retain itself over time. It is reliable. MAD is mainly served for two purposes: to select one technique among several forecasting techniques and to estimate standard deviation of forecast. Tracking signal is mainly used for two purposes again: to make sure that the summation of the differences between actual and forecast divided by MAD remains within upper control limit and lower control limit. And upper control limit and lower control limit in reality is set to +5 and -5. So it wants to make sure that tracking signal remains between +5 and -5. And the second main purpose of tracking signal is to make sure that while the tracking signal is within upper and lower control limits, it also does not show any systematic component. It is completely random. I think this is enough for our first introductory session on forecasting, and I really encourage you to solve the assignments. Thank you for your patience.